Welcome to this lesson on solving compound inequalities. Today, we'll explore how to solve compound inequalities step by step with 3 detailed examples. We'll learn to graph our solutions, express them in set builder notation, and write them using interval notation. Let's start with our first example. Example 7. Solve the compound inequality. 2x is greater than 10 or 2x minus 3 is less than 5. First, let's solve each inequality separately. For 2x greater than 10, we divide both sides by 2 and get x greater than 5. For 2x minus 3 less than 5, we first add 3 to both sides to get 2x less than 8. Then we divide both sides by 2 to get x less than 4. Since we're dealing with an or compound inequality, we take the union of our two solution sets. The union includes all values of x that satisfy either x greater than 5 or x less than 4. Let's visualize this on a number line. For x greater than 5, we have an open circle at 5 with an arrow extending to the right. For x less than 4, we have an open circle at 4 with an arrow extending to the left. In set builder notation, this is the set of all x such that x is less than 4 or x is greater than 5. In interval notation, we write this as the interval from negative infinity to 4, union with the interval from 5 to positive infinity. Now, let's move to our second example. Example 8. Solve the compound inequality. 6 times open parenthesis x minus 2 close parenthesis is less than or equal to 10x and 5x is less than 10. Let's solve each inequality separately again. For 6 times open parenthesis x minus 2 close parenthesis is less than or equal to 10x, we first distribute the 6 to get 6x minus 12 is less than or equal to 10x. Next, we subtract 6x from both sides to get negative 12 is less than or equal to 4x. Finally, we divide both sides by 4 to get x is greater than or equal to negative 3. For 5x less than 10, we simply divide both sides by 5 to get x less than 2. Since this is an compound inequality, we find the intersection of our two solution sets. The intersection includes all values of x that satisfy both x greater than or equal to negative 3 and x less than 2. Let's visualize this on a number line. For x greater than or equal to negative 3, we have a closed circle at negative 3 with an arrow extending to the right. For x less than 2, we have an open circle at 2 with an arrow extending to the left. The intersection is the region where both conditions are true, which is from negative 3 up to, but not including 2. In set builder notation, this is the set of all x such that x is greater than or equal to negative 3 and less than 2. In interval notation, we write this as the closed open interval from negative 3 to 2. Let's tackle our third and final example. Example 9. Solve the compound inequality. 1/2 x is less than 3x plus 5 or 6x is greater than or equal to negative 18. Let's solve each inequality separately once more. For 1/2 x is less than 3x plus 5, we start by multiplying both sides by 2 to get rid of the fraction. This gives us x is less than 6x plus 10. Next, we subtract 6x from both sides to get negative 5x is less than 10, dividing both sides by negative 5. And remembering to flip the inequality sign when multiplying or dividing by a negative number, we get x is greater than negative 2. For 6x is greater than or equal to negative 18, we divide both sides by 6 to get x is greater than or equal to negative 3. Since this is an or compound inequality, we take the union of the two solution sets. We have x is greater than negative 2 or x is greater than or equal to negative 3. Let's think about this carefully. Any value greater than or equal to negative 3 includes all values greater than negative 2. So the union of these two sets simplifies to just x greater than or equal to negative 3. On our number line, we show this with a closed circle at negative 3 and an arrow extending to the right forever. In set builder notation, our solution is the set of all x such that x is greater than or equal to negative 3. In interval notation, we write this as the interval from negative 3 to positive infinity. Let's review what we've learned about solving compound inequalities. First, solve each inequality separately by isolating x. For or compound inequalities, we take the union of solution sets, which includes values that satisfy either condition. For and compound inequalities, we take the intersection, which includes only values that satisfy both conditions. Remember to represent your solutions on a number line, and express them in both set builder notation and interval notation. When working with inequalities, pay attention to direction. Remember to flip the inequality sign when multiplying or dividing by a negative number. With practice, you'll become more comfortable solving these types of problems.